Okay, so now one neat thing about what we've just done is that the same model will work regardless of how many levels there are in our categorical predicted variable. And so this is the trade-off between, we talked a bit about making your models general versus specific. So calling things like y and x versus calling them what they actually are. And there's good and bad sides to both of those. So if we use generic names for our variables in the last model, like y and x, then we could use exactly the same code with a different data set. But since we labeled them things like height and sex, we obviously have to change them a little bit. But the structure and the logic and everything else is exactly the same if we have one metric predicted variable and one nominal predictor variable, regardless of how many levels there are in that nominal variable. So let's work through an example. And this one, the code is all there, but in this presentation, we're not going to go through all the steps again, because I think you get it. So the data we're going to look at here, these are faculty salaries from an unnamed Midwestern university. This data set is from Krushke's book on doing Bayesian data analysis, and I believe he is at Indiana University. So my guess is that it's from his university, but I'm not sure of that. So this data set you can get from Brightspace. So we can read it into R using the read table function, as you see here. And we can just take a peek at it using the head function and see what it looks like. And you can see what they have is the department for each individual. This is business and finance. And that's under the org. And the field name for that is org. The name of the department is given in this next field. There's positions, so assistant professor, associate professor, endowed professor, and so on. And then the salary of each individual. And so, of course, what position a person is in, a faculty member is in, is going to influence their salary. But in some schools, so does the department. And so what we're interested in today is just the effect of department on a faculty member's salary. And again, this is not from SMU. I think SMU's, we have a very strict collective agreement that wouldn't allow something like this to happen, but not all universities do. So we can take a look at the structure of this data set once we read it in. And so we can see it's a data frame, and we have 136 observations. So we have data on the salaries of 136 individuals. And we have, again, the different fields that are in this data frame. So again, let's look at the relationship between salary and department, which here is abbreviated with ORG in the ORG field. If we look back here, originally R has defined this as a character, but remember, to make this a categorical variable, we need to make it a factor. And so we can make that org field a factor using the as factor function. Again, so we did this before as well. So we're just replacing the original org field with that as a factor. And so now if we look at the structure of this data frame, you can see that it's changed this variable to a factor, and it's saying it has 4 levels, business and finance, chemistry, there'll be English and psychology, and then the numbers associated with those. So first we can plot the data. Again, we're not going to go through all the different plots. We'll just look at a box plot of these. So looking at salary versus department. And so you can see there's quite a bit of difference, right? The people in business and finance are making quite a bit more than the people in the other departments. And the poor English professors there are in the worst shape. They're making the least amount of money, and less than half, it looks like, than those in business and finance. So this is a little bit striking. I'm sure the English department isn't very happy about that. So let's say we want to test and see, is there an effect of department on salary? It clearly looks like there is. So again, we could do this with the frequentist approach. So when you're analyzing data with a metric predicted variable and a categorical predictor variable, and we have multiple levels, more than 2 levels in that variable, that's an ANOVA. So again, hopefully you're seeing that we can all think about these as we can take a principled approach to model building by just thinking about what the data are instead of thinking about all these different tests. But anyway, I'll show you how to do this. So to do an ANOVA in R, you just use this AOV function. Excuse me. And then you write out this equation the same way you do for a linear model. So we want to know salary given this org field, which is the department. And so I'm just going to write the results of this analysis into a variable called ANOVA test. And there's a few ways that we can view the results of an ANOVA. So one is we can print model.tables of our ANOVA test. And what this will do is show us a table of the effects. This is the effects of being in each department on salary. And what it's showing you here, well, there's a few things. This is the sample size. So there's 21 individuals in business and finance, 35 in chemistry, and so on. Now what this is saying is how being in each of these departments bumps your salary up or above or below the mean salary across all departments. And so you can see in psychology, they're making on average $6,000 less per year than the average across all departments. Whereas in English, they're making about $42,000 less per year. Whereas the business and finance faculty are making about $86,000 more per year than the average across all of these departments. So this gives us a table of the effects. If we want p-values, we can just do summary and then ANOVA test. And this is testing the null hypothesis that department has no effect on salary. And so we can see that's very low p-value, so we'd reject that hypothesis. So again, we can also do the same thing with a linear regression, even with a frequentist-based linear regression. So we can do it that way. And so here again, we're using the LM function, the linear model function in R. And then this equation is the same, so salary given department. And we're going to call this model. And we can look at the results from this by just doing summary and model. And so here we can get our coefficients. Now, these are a bit different. They mean something different than what they did in the ANOVA. Remember, what R does when you have a categorical predictor variable is the intercept. It actually uses that first one as what it calls the intercept. And then all the other effects are the difference between that level in the category and the one that it's chosen as a reference. So the first one was business and finance. That was given the indicator 1 in our factor. And so this is the mean salary of someone in business and finance. And then what this is, it's the mean difference between a salary in chemistry and that in business and finance. And then this p-value, so this p-value is saying, is this salary different than 0? Well, duh. And then what this p-value is are the salary in chemistry different than those in business and finance? So this says yes. So the null hypothesis being tested here is that there's just no difference in salaries between these. So you can see they're all different relative to business and finance. So that's what they're testing here. So those are ways that we can look at these data in a frequentist approach. Of course, we can also do a Bayesian approach. And again, we're not going to go through all of this. The code is there, but I think you'll get the idea. So the first thing we want to do is standardize the salary data and then get our sample size. So this is all the same as what we've done. We can organize the categorical data. So I'm just going to make a new variable called dep for department. That's going to contain the numbers associated with the factor value of department. I'm going to get the departmental names using the levels function. So here's business and finance, chemistry, English, and psychology. And then the number of levels. So it should be 4. So dep levels is the length of this department name. So we have 4 different levels in this categorical variable. Then we can create the data as a list and send it to Stan. So here, this is all just standard. And then build the model. So again, this model is exactly the same as the one we've done before. Just because we have a different number of levels in this categorical variable, we've written the model in a way that it doesn't matter. It takes that into account. And so we don't have to change it at all, except that since we use specific names, since in our last model we use height and sex instead of Y and X, and now we're using salary and department instead of Y and X, we do have to change our model, but just to change the variable names. The structure doesn't have to change at all. So here is our data block, where all I've done, I haven't changed the structure of any of this. All I've done is change the names as needed, right? So department and department levels and things like that. But because we've set this up, right? So like for our priors, it's 1 for however many levels there are. The fact that we could have 100 levels here and this code would stay the same because we're setting it up in a way that will handle many different levels. So our model structure stays exactly the same regardless of how many levels we have. We can just change the variable names as we see fit. Then we can run the model, and like I'm going to skip the testing the Markov chain Monte Carlo and the prior predictive checks. All those were fine. And then we can look at our results, right? So here we have our posterior probabilities associated with the effects of department on salaries. And we can see big differences between most of them. We can also plot this using the GG ridges. Again, I think this is a nice way to compare the whole posterior probability distributions across levels in a categorical variable. And so this, we can see business and finance way more than the others. And English is the lowest. What would be interesting is to compare chemistry and psychology. Like, are these that different? And so again, with these, we can pair them up. Like, now that we have these posterior probabilities, we can pair them up however we want, or not even pair them. We can group them however we want and do comparisons and get posterior probabilities of those differences. So for example, if we want to know the posterior probability of business and finance versus everybody else, we can just combine all of these and then compare that to this posterior probability, and we get a posterior distribution of the difference between those ones. And we could compare these two. So you can compare, you're not limited to just pairs. You can compare, you can group them however you want, as long as you kind of combine them appropriately and do your comparisons that way. Then we can do our posterior predictive check. Again, all the code is there. This is the same idea as before, where I randomly select 20, well, not randomly, 20 individuals have been selected kind of equally spaced throughout the data set. Here we have the predicted salaries, which is based on their department. So everyone in the same department is going to have the same predicted salary. And then in the red dots, we have the actual salary. So you can see there's this person in business and finance is getting not business. This is business and finance. I don't remember which one this would be, but somebody's getting paid a lot more than we expect them to. But again, these are 95% highest density intervals. So we expect 1 and 20 to be different. So everything looks good here. And again, the details are in the code. The point is that, again, so with our same model, we've done kind of what you would do for a t-test and for an ANOVA. But again, by just thinking about our data and building an appropriate model, we can conduct appropriate analyses instead of memorizing different types of tests. And that's part of the power of taking this approach. Okay, that's it for today, and I'll see you guys soon.